All right, so I get a little notice that there's a software update available, which I'm going to ignore for right now. Okay, so I've started making the lab. I'm just going to kind of walk through some of the things I talk about, but you'll have a document in the lab that I've typed up a lot of things I'm going to say for the next 5 minutes here. So who here has used ArcGIS ArcMap before? Raise your hand. Okay, good. So some of the things are similar. Who's used ArcGIS Pro before? Okay, there's some of you who have already used ArcGIS Pro. Okay. All right. So I'm going to talk about this assuming that you've had ArcGIS, that you've used ArcMap before, but if you haven't, I don't think that if there's something that I'm saying that you totally don't understand, then stop me and I'll try to fix that. Okay? So ESRI refers to ArcGIS as being project-based. So every time you open it, you have to either open an existing project, you can see all the projects I have open, or create a new project. You have to do one of those two things in order for it to work. Okay? In this class, you can think about each week's class. Each week's labs could be a new project. You could just call the project the exercise number for this class. So typically, when you open the software, you'll get a message like this. You'll have to log in. And then you hit the blank, and it'll create a new blank project. So I'm going to hit blank right now. And then you can type your project right here. So I can just call this SAEX1. That's what I call it. You can call it whatever you want. It really doesn't matter what you call it. I called it SA, which stands for Spatial Analysis, _ exercise 1. And then it stores it in this location. Okay? Now, what it does is actually similar to, I can't think of a software package that you all would be familiar with that does this, but it will actually create a folder to store all of your project materials in. So what it's doing is, as soon as I press OK, it's going to create a folder for the project. You can actually say, I don't want it to do that. Unclick this. Okay? But if you have that clicked, it's going to create a folder, which is the default behavior. I think it works well for this. You could store that folder in a different location. This is the location on disk where it's going to store that. Now, some people like to use thumb drives. Anybody here going to use thumb drive this semester? Okay. That's okay, but I do want to warn you that this semester, raster data can get kind of bulky. And when we start processing the data, it's going to take, let's say that it takes 3 seconds to do an operation when the raster is stored on the hard drive. It's going to take about 9 seconds for that to run. It usually takes 3 times the amount of time to run on if the raster is actually stored on your USB thumb drive. So that's not a problem if you're willing to tolerate it, but some of the larger data sets are going to take several minutes to run. I'm not going to use any data sets that hopefully that take hours to run or anything. But if it takes 10 minutes to run, it's going to take 30 minutes to run on your computer. So keep that in mind. And what I would probably do myself is either always use my laptop and store the data on my laptop locally. That's one option. Another option is to just use a portable hard drive. A portable hard drive now, they approach the same read-write speed, although they're still slower. But they approach the same speed as a thumb drive. But what I mean is an actual portable drive, not just a thumb drive. Those are considerably slower. And then the third option is the option I like the best, but not everybody here might be comfortable doing it, is to just copy this project folder. When you're done working, close ArcGIS, close ArcGIS Pro, and then find the folder on disk. So see, as soon as I hit OK here, watch this. I say OK. Oh, I forgot where I stored it. But But as soon as I create that, I think it'll show me the path. So I hit OK, and if I go to folders, it should tell me, yeah, there's the path right there. If I hit view metadata there, is that gonna? No, that's not gonna tell me. But I saw the path there for a second. See the path? Users, George, documents. So it's in my documents. So if I go to my documents, ArcGIS, see how I go to my documents, ArcGIS, and projects. It's right there. That's the folder that just got created. I can tell it just got created because it says 1/24/2019, 2:59 p.m., which is a minute ago now. So it created that right there. So this is what I would do, is actually work from that folder, and you say copy, and you copy that onto your portable thumb drive. Like, let's say I had a thumb drive right here. I had one. Probably until I kicked my backpack. I thought
You want to borrow one?
I think I found it. Yep. It's one of those like really tiny ones like this. Usually I just leave it plugged in, but I have so much stuff plugged in. So I plug my portable portable thumb drive into here, like that, and now I have that. So this is my D drive, and I could just take this and copy it over. See, it says copy to D. I don't need to do that right now because there's nothing in it right now. It's just kind of empty. There are a few files in there, which we'll talk about. But now I have a backup. And then if I come back and somebody has erased my my copy that's local, then I can just recopy it there before I open it. And then everything will work. Okay. All right. Now that assumes, though, that you store everything that you're doing in that folder. So you need to put it in that folder. Okay. So we'll talk about that in a second because I've downloaded some data that I want to demonstrate with. So that'll all be on the video if you want to watch this later. Okay. So I've copied that over just for fun for right now. But let's take a look at these files that are in here. So by default, it creates 3 files. One is just the project file itself, the APRX file. That's the file that kind of, it keeps track of everything. It stores the information about where all of the other resources that you're using are stored. Okay? So if you've used ArcMap before, it's very similar to the MXD file. It doesn't store the data itself. It only stores the links to the data. So that's why I was saying, if you want to make sure you keep all your data, make sure that you put all your data in the same folder. Or more complicated, you could actually copy all the files from all the disparate locations that you've stored your data on, but don't do that. Store all your data in that folder, and then you'll be all set. Okay? And then it also creates, by default, it'll create a toolbox, an Arc toolbox. And we're going to use toolboxes a little bit in this class. But one of the things that I've decided are, there's a new way to interact with raster data every year, it seems like now, in the software. So rather than teaching this class as a how to use model builder class, we're going to talk about interacting with raster data, and we're going to learn a little bit about using it in our toolbox as a toolbox in model builder, and then we're going to learn a little bit about scripting, which is another way to do it, and we're going to learn a little bit about doing it in this new way that's called a function chain, or a raster function chain, and that's kind of the default user interface now in ArcGIS Pro. And so we'll have all those ways. And this lab is actually going to introduce each lab, the lab's going to introduce each of those as a concept today. And we're going to kind of put off scripting because we're going to do that later, but I'll very lightly introduce that today. They're all lightly introduced, but that's the least lightly introduced. There's a whole week on just Python scripting, and there's a whole course on Python scripting if you want to take that course. It's 518 is what it's numbered. No, that's this course. 468, 568 is what that's called. All right, so by default, your map will look something like this. If you don't have the catalog pane already open, you can open it under View. You can open up anything that doesn't appear there. So I can open up the catalog pane. The one I closed, which I didn't even mean to close, was the catalog view. I can open that back up. I could open up the Python window, which is already open, but if yours isn't, like if yours looks like this, you can hit the Python window. We are going to talk about that a little bit today. This is kind of like the beginnings of the lab. Okay, and then we've got a few other windows. I don't use the tasks window very much, but it's there. You can create new task items, and they're saved in your project. You can like check them off. Oh, I got to do this, 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 and this. It's nice to have, but yeah. And then you have to have a special extension to run that, so that's why it's disabled. And I don't even know what reviewer rules is personally. I guess it's for reviewers, but we're not gonna focus on that one anyway. So what we are going to talk about a little bit is this catalog pane. The catalog pane is most similar to Windows Explorer in that it allows you to kind of see what GIS data you have on your computer. Now, by default, it only sees into this folder that you just created when you created the project. So it only sees into there. And right now, you don't have anything stored in there. It says in Windows Explorer that you have all this data, but that's just the kind of background information that it needs to create a file geodatabase. See, there's no data sets in that file geodatabase. Who's used a file geodatabase before? Raise your hands. Okay. All right. Tell me what a file geodatabase is. Somebody that raised their hand.
It stores the information so you can create them to store all the information for your project.
Okay. Yeah. It stores GIS data. You can also store tables in it, but yeah, it stores the information that it stores. That you said information is typically GIS layers. Stores GIS layers. And I have included in the download today I don't know where it went, a geodatabase. It's called, well, when you download it, it's called lagunabeach.zip. Okay? So when you download this first file, first one we're going to deal with, it's called lagunabeach.zip. I'm not going to download it again because it took a little while to download the first time. But if I show that in the folder, it'll show me where it is on disk. It'll typically be in your downloads directory. And then if I double click on it, I can see that it contains another folder. But I know that this folder is a special type of folder that is what's called a file geodatabase. The reason I know it is because it's got that extension .gdb. And if you open this up in Windows Explorer, there's a whole lot of nonsense that you don't know what it is. Okay? To properly look at this, you need to look at it in ArcGIS Pro or ArcMap. So in order to do that, I think the best way to do that is to copy this into your project folder. So I'm going to copy this, see this lagunabeach.gdb, I'm going to right click, I'm going to copy this, and I'm going to put it in your in my folder, which we decided was in Documents, ArcGIS. It really doesn't matter where you put it. Essay Exercise 1. I'm just going to store it right next to the Essay Exercise 1. So now I've got another geodatabase in there. 2 geodatabases. So by default, all of my, when I run something and I create a new layer, it'll be saved in the SAEX1 geodatabase. But I can draw from this database. So now let's go back to ArcGIS Pro. And now you can see that inside of folders, go inside of folders, and I expand folders, I can see the Laguna Beach geodatabase. If I want to see it up here in the databases section, I need to right-click on databases and say Add Database. It doesn't know that it's there until I actually choose it and I say lagunabeach.gdb. If you don't see it in the list, you can hit this. This is the refresh button. It took me a long time to find the refresh button in ArcGIS Pro. Because, you know, in like Chrome or Microsoft Explorer, Internet Explorer, it's like right there. It's like big. But yeah, you hit that refresh button and then it'll show up. Then you can choose that and it'll, now lagunabeach.gdb is in there. So now I have 2 geodatabases. You notice, look at how there's a little icon next to the SAEX1. That little icon is a house, and what that means is it's the home geodatabase. That means that by default, things will go there. We could change it and make that the home, make that the default. And then when we ran anything, it would show up in that folder, that make default folder. I mean, geodatabase. I'm not going to make it the default because I want to store my outputs separate from my inputs. So my outputs are going to go in there. Okay. So if you've used ArcMap before, ESRI likes to say it's map-based, right? So every map document, it contains a single map. In fact, you can add like inset maps and submaps, but you only have one print-off, one layout is what it's referred to deal with. So you only get to make one map with all of your maps. So ArcGIS Pro, though, isn't map-based. It doesn't even have a map open by default. So there's no map there. If I want to put a map on the page, I have to go to the Insert tab and say New Map. And there is the new map. So now I have a map. All right. So now let's say I want to look at some of this data, some of this Laguna Beach data. I've used this before in another class. And I plan to use this later. You'll notice that there's a lecture called Cellular Automata. We're gonna model fire spreading, and it's a simplified version of actually a few different researchers that modeled fire using the Cellular Automata technique. But we're going to do that later in the course. So this is the data for that lab, but it's also the data for this lab. So we're going to look at some of the data. I'm going to start out by looking at this image LB data set, because that data set is going to be the most familiar for those of y'all who have taken our remote sensing course. So there's a few different ways to get this in there. One of the ways is to just drag it from the project over into the map. So I just dragged it into the map. And now you can see we've got some high resolution imagery with the One of the things ArcMap does is there's always a default base map unless you turn it off. So here I've got the topographic default base map. So you can see that on there. One thing, this is a review for those of you who've taken my other class. I'm sorry about that. One thing though is if you zoom out, you'll notice that the projection changed, right? You can no longer see the entire world. It's because this data set has a specific projected coordinate system that it's using, and that projected coordinate system distorts those places so much that they're basically wrapped around behind the Earth. You don't see them anymore. Okay. In fact, I didn't really mention this in the lecture, but projection is, maybe I did mention this, I feel like I'm repeating myself, but the projection is actually of utmost importance when you're dealing with raster data sets, because when you change anytime you change projection, it's going to change the cell size, because the distortion occurs everywhere. It's not just like taking points and moving them to new positions. Okay, you're distorting them. You're bending the map when you change projections, because you're trying to make the area that you're working in as flat on the surface of the Earth as possible. That's your goal when you do a projected coordinate system. And so when you do that, when you change a projection, you're adjusting the Earth and you're flattening it right there where you're going to use it. So this is a pretty small area, so luckily we can make it fairly flat. I'm not sure what the distortion is, but if I want to know what the coordinate system that's being used in, I can always right-click on the properties for the layer, and that's not much different than it is in ArcMap. So I can look at the source data, and I can see some things. So the raster information will tell me how many rows and columns I have. It'll tell me how many bands my data set has. I have 4 bands. All right, quick quiz here. How many am I actually looking at the same time right now? Yeah, right. I'm looking at 3. I can only see there's only 3 different color primaries that we have. So everything has to be either red, green, or blue. We're displaying it as red, green, and blue. It's a little bit of a concept to wrap your head around, but a lot of you have been dealing with this for most of your life, computer screens. But the computer screen here, every pixel is shooting out red, green, or blue pixel, and red, green, and blue pixel. So for every pixel, there's actually 3 color guns: a red color gun, a green color gun, and a blue color gun. Okay, and that's even outside of this particular raster data set. So when we display a raster data set, we need to transform whatever's stored in that raster data into red, green, and blue. What's the bit depth of the display, by the way? What are those color guns? Those color guns are actually a digital number is being converted to how bright it is. How many different brightness values are there for red, green, and blue on the computer screen? Most computer screens. Yeah, there's 255 different ones. Sometimes people say, there's 256 different ones because it starts at 0. So you've got 256 different brightness values. You could say 255 because I guess 0 means that it's not bright at all. It's 0. It's dark. Okay? So every pixel on the screen has to get a value from the raster data set and convert the value that it gets into a display value on the screen. So if we use the identify tool, which actually that's one of the differences. There's no identify tool anymore for ArcMap. You just click on the map, and it will actually tell you what the pixel value is. Here it's that one that we clicked. The pixel value means the value on disk. So 67, 63, 58, red, green, and blue. Now, we don't know what these actually mean, but I can tell you that they actually mean red, green, and blue because this is showing, if you were up in an airplane, do you think this is pretty close to what you'd see? It's pretty close. You might see some slightly different variations in the colors. It's what we call a natural color composite. So red is displayed as red, green is displayed as green, and blue is displayed as blue. Okay. Now, what's actually stored on disk is different than what you're actually seeing. 102, 93, 81 are the values that are actually being displayed for that particular pixel. I'm going to pay a little more attention to the pixel I'm picking this time. I'm going to pick one of these reddish, orangish roofs. You know, California, there's a lot more of these than there are in our area. I'm going to click one of those, and you can see that the value for red is much higher than the other values, and they're all pretty high overall if they go from 256. If I select in this blue pool, see how low the red is now, and the green and the blue are both pretty high. RGB, yeah. They're pretty high. In fact, green is actually higher. That's probably why it looks a little aquamarine, because it's a mix between those two values. Maybe I clicked on a pixel that's a little more aquamarine than, maybe I'd click over here in the deep end. Yeah, see now, oh, now the green's still pretty high. All right, so that's looking at an RGB symbolization of that data, of those multiple bands. So in ArcGIS Pro, if I click over to symbology, I can change the primary symbology right here. I've got a few different choices. One is to stretch it. Stretch implies that I only want to look at one of the values at the same time. So here I'm only looking at band 1 now. So now I'm only looking at one data set. I'm not displaying 3 data sets at a time. So this is perhaps a little bit, maybe I should have started with this type of a data set and progressed on to a multi-band data set. But here I'm displaying just band 1, which I mentioned before is the, I think it was the red band. Let's see, which one was this one? Let's change it back to RGB. So this building is pretty red. Let's switch back to stretch. The building looks kind of dark, but let's look at it in band 3. Which one looks brighter? Yeah, okay, so it's definitely the red band. You see how this roof got darker between 1 and 3? Okay. So what's happening when I switch between 1 and 3, or between 1 and 2 by accident, is that the original data set is being inspected, the raster data set's being inspected, and I'm getting a value from every single pixel. I'm getting a value, and that value is being converted to a grayscale value, and to do that, it's displaying the same red, green, and blue pixel. Anything that shows up in gray is, if it's dark, that means it's got a high value, a low value, like 555. If it's bright white, if it's the brightest white possible, it's 255, 255, 255. I'm going to click on this guy, and it's going to tell me here is the original value, and here's the value that's being displayed, 217. Now, both of these cases, there's a discrepancy between what is stored in the computer and what's actually being displayed, and that's for our benefit. Okay? The stretch, what it does is it improves the contrast for us. We can look at the history. If you look at the histogram here, what's a histogram? What is a histogram just in the general sense? If I said, here's a histogram of the heights of all of the people here at USM, okay? Then the x-axis would be what? in that case? Yeah, the x-axis would be the heights of the people, okay? Here, the x-axis, these are the values in the original raster. So these are the values in the original raster. They range from 0 to 254. In other words, what it's saying is that there's no 255. It's the highest it gets, okay? All right, the y value here in any histogram is the count. So what this is saying is that there are that many, what is that? 1,678,910. I guess I'm at 37. There are 37s in the data set. So there's a lot of them. There's less. Here I'm at 200 about. I'll get to 200 exactly. 200. And there's only 230,000 of those values in this whole image. There's a lot of pixels in this image, but there's less of those. So this histogram is saying, oh, there's a lot less. So there's a lot less bright pixels than there are dark pixels. This is just showing us the information now for band 1. I think I'm still on band 1. Yeah, I'm still on band 1. So what I can do is, by default, it stretches the histogram so that I'm going to cut out anything that's above or below 2 standard deviations, and I'm not even going to display those things. Well, okay, I'm going to display anything below 2 standard deviations as the darkest pixel possible, and anything above 2 standard deviations as the brightest pixel possible. So I can change the, so this is not standard deviation, this is percent clip. So it's basically cutting off the lowest 2% of the data and the highest 2% of the data. I could change that so that I choose the lowest 20, the lowest and the highest 20% of the data. So now I update that. One of the things that you could say is that I've increased the contrast, but at the expense of blowing out the very highest values and the very lowest value. Well, so 20 plus 20 is 40, right? So 60% of the values I'm now spreading across the entire range of possible output values. So now if I click on an area, let's say right here, now the pixel value 65 is much different than the stretch value. 65 has been increased all the way up to 120. And then maybe another way to say this is if I change these both values both to 0, if I change both of these to 0, then I'm going to see this is the data as it should appear. In other words, it's a one-to-one relationship. In other words, a 1 on disk is a 1 in that's sent out of the monitor, and a 74 is 106. Okay, well, it's not quite the same because of the fact that the range doesn't. It's still stretching the entire range. If I wanted to say I don't want to stretch at all, that's min-max. Let's see if I change this to like 10.
So what the purpose of stretching is to correct the contrast so that you can visualize it better?
Exactly. Yep. And so if by default the standard deviation stretch is 2, but if I change this to 1, it's also still cutting off those outside edges. So sometimes you might have a data set. Well, let's see if I've loaded one. Sometimes you might have a data set. Whoops. Let's change the stretch to standard deviation 1. Back to 2. Seems to be a bug in the program. It's like every time it keeps stretching. It keeps stretching the data set further and further. Let's see if that was just a fluke. So if I change this to standard deviation, I'll change this to 1. I think that was, I don't know how I got it to do that, but it looked like to me what it was doing is every time I was changing the standard deviations, it just kept taking what was left and applying the slice on just that. So there are sometimes flukes in software, glitches, and so in that case, I just reloaded the layer. If it was still doing it after that, sometimes you might have to shut ArcGIS down and start it back up or something. Now, I can change the color scheme. So here, I could take the data that's displayed in band 1 and put a different color scheme, so it's not just grayscale. Here it's going from green to red, or from, I could just go from one solid color, I think. Let's see if there's one of those. I don't see one of those. Oh yeah, there's purples or something. No. Anyway, I don't see that. This is referred to usually as a pseudocolor. Pseudocolor is when you're taking a raster data set and just assigning an arbitrary color scale to it. So RGB would be a true color, and we could actually change it so that instead of showing band 1 as red, we could show the near infrared band. So you've probably seen something like this in a remote sensing class if you've taken a remote sensing class. This is called a false color image. So we're still displaying color to color. It's just we're mixing which colors are displayed as what. So this is the reason why it shows up red in all the vegetated areas is because near infrared is reflected a bunch of energy back to the sensor in this case. All right, so notice that under the stretch we have a bunch of different types of stretches. I'm not going to go through each one of them, but basically what they're doing is taking only part of all of the possible displays and assigning a new value for all of those displays. If you ever have a data set that comes up mostly the same color, it might be that it's just not stretched appropriately. And I'll get to an example of that later. Let's look at a few of the other data sets. Oh, but before we move on, finally, I want to go into the properties and look at the bit depth. So the pixel depth is the bit depth here. It's 8-bit data. What does that mean, 8-bit? Well, that means that you can store a number from 2 to the 8th in it. So it's an unsigned number. So it's a number from, what's 2 to the 8th? 256. So all of the numbers will be a number, all the numbers stored in this raster data set will be numbers from 0 to 255. However, let's look at a different data set. Here's my elevation data set for the same area. Now this data set, if I zoom out here, you can see it represents elevation, right? Just like the map, the coarser map of Mississippi. But the values range from 2 to 295. What units do you think those are in? Yeah, it is kind of high. But what's kind of crazy? Look how far away we are from the ocean. There's the ocean, and this is the highest area right here. So you think, oh, maybe it's feet, right? it's actually in meters. It's not always accurate. The metadata is not always accurate is one thing to keep in mind. This is accurate though. So there's quite an elevation change between the ocean and this area up here. In fact, there's an elementary school that my nieces and nephews go to right here that's called Top of the World Elementary. But
Why you don't want to have fire followed by rain like that.
yeah, yep. Yeah. So so you can see all the way up into Orange County, and you can see down there. That's why they refer to it as that. It's not really the top of the world. It's not nearly as tall as Everest. But look at the cell sizes stored in here. That's accurate. Now look at the pixel type here is floating point. So I told you there's two basic types. There's integers, which the last one said unsigned something. I forgot what it said, but it's an integer, and floating point numbers. So these are floating point numbers. It's 32-bit floating point numbers. Now that does mean that the total number of values you can store are 2 to the 32nd. However, when you start mixing floating points in there, it doesn't mean that the number can get from a certain value to a certain value. It has more to do with the precision of the floating point number. Okay. So the more bit pixel depth you have, the more precise your floating point can be. So it doesn't make a whole lot of sense to have a really, really precise floating point number for elevations, especially if your elevations aren't accurate, because we're doing meters, right? So what is 2 decimal places in meters? We're already talking about millimeters, right? Yeah. So you don't need 3, 4, 5, 6, 7, 8 decimal precisions. You will find raster data sets on the internet. You'll find them of elevation or maybe salinity or any data set that exists out there. Sometimes in order to save space, instead of doing a compression, what they'll do is store the number as a floating point number, as an integer number, but multiply it by 100. So let's say you only need 2 decimal places. It's like with temperature. Temperature is actually a really common one for this. Once we get down to hundredths of a degree, there's not really, in most applications, especially in GIS modeling applications, a tenth of a degree is probably okay. So if we just multiply degrees by 10 and then truncate the decimal, we can get a much smaller data set, but still have the same level of precision. We don't need to store it as a floating point number. So sometimes you'll see that. In fact, we'll use a data set like that in this class. So, but this is a real floating point number, got a pixel depth associated with it. Sometimes the metadata will actually show you how big it is on disk. I don't see that here, but we can figure that out. So it's just 1104 times 702 times 32. That's how many bits there are in this image. And then we could just divide that by 8 to get the number of bytes, divide that by 1024 to get the number of kilobytes, divide that by 1024 to get the number of megabytes. Okay? You're not going to have to do that. But what I'm trying to show you is that the number of rows and columns and the bit depth is exactly what determines the size of your data on disk. There's nothing else that determines that. Okay. All right. So here in the spatial reference information, we can see what the coordinate system information is. Doesn't look like we're going to. It doesn't even look like it shows us what the corner of the data set is. There are some formats, I think, that show you. Okay, well, here it's showing us what the extent is. We've got the top, the bottom, the left, and the right. It really only needs to store on disk 2 of those numbers, either the top and the left, or the bottom and the right, and then the cell size, and that's what it's using to place it on the map. So now with this elevation data set, if I look at the symbology for elevation, I've got choices: stretch, discrete, classify, unique values, vector fields. We're not going to talk about vector fields for a little while, but I will try to incorporate them in the class. But basically, you can store the direction and the magnitude as two different rasters, and then make a vector with that. All right, so discrete. That's what discrete shows up. Number of different, a color scheme. And so it's mapping all those values that range from whatever to whatever. In our case, I'm going to expand this so I can't see them anymore. But if I want to look at the properties again, I could see what the min and the max are somewhere. That's statistics, right? So the minimum value is 2.54, the maximum is 295. So it's taking those values, all those different values, and it's displaying them on this axis. However, it runs out of values and just displays nothing above that point. So that's not a very good choice for that particular one. Classify is another way to visualize data. And what that does is it takes ranges of data and assigns them the same color scheme. So in other words, here, everything up to 69, or sorry, everything up to 69 is yellow. Everything between 69 and 116 is now orange. And everything from 116 to 162 is a darker color orange, and so on. Yeah. I mean, yeah, a heat map is a way to count occurrences. Yeah. This is just kind of slicing your data up. Another way to think about these actually, the boundary between these, in this case, what would we call the line that forms the boundary between these two zones? What's the generic term for that?
It's not ISO line.
Yeah, the generic term is an ISO line. Great. Now when we talk about it as in elevation, there's a specific term for that ISO line. Starts with a C. A contour. So a contour line is the line in between this. So basically, it's an alternative way to visualize contours, but you're filling in the areas in between the contours. This is often used like when we want to. You'll see, maps. I don't know why I picked Katrina, but it was a long time ago. So you'll see a map like this, even now, like whenever a hurricane comes, and you'll see what are these? I forget what when they represent pressure. Or no, actually these represent speed. So the 80 miles an hour is right here, 50 miles an hour here. I still don't know what they're called when they represent speed. Yeah, but yeah, if this was a raster data set that represented wind speed, the way we would create this is to use the classify dropdown. And in that case, we usually want to select equal interval. In other words, the lines would be equally spaced so that you could see what happens when the lines get close. What does that mean? In other words, like this area right here, see, it goes from orange to, yeah, it means it's steep. And so in wind speed, it would mean that the wind speed changes rapidly as you move through there. So it's like prompting the user to understand the degree of change that's going on. Okay, so yeah, you could change different intervals. We talk about this in your introductory class, right? You should have talked about different interval methods. So natural brakes just tries to find, natural breaks in the data. I think we can actually look at the histogram, or no, I guess we can't look at the histogram here, but the ones you're going to use the most often would be equal interval, and you might use manual. Manual would let you choose your own values. I think you can just click, yeah, you can just change the value yourself. So you can just change this to 80 and hit enter, and now you've got a different value there. But quantile is another useful one, and probably not as useful in this case, but what it does is it says an equal number of cells will have each value. Okay? So for elevation, that probably wouldn't be as necessary, but there would be cases where basically if you want there to be as much contrast in a classify scheme, you would choose quantile, because what it'll do is make sure that you have an equal number of cells that are each color. And then unique values so it's going to tell me here, I can't really do unique values because there's so many different unique values. It's elevation after all, right? So let's add a different data set that can do unique values. That one is, yeah, I'm going to do flow. We're going to learn about actually what's going on and how this is created. But this data set, every cell has been given a number that represents which way water would flow out of that cell. So that's what the values represent. We're going to learn about how to create that later. But that's what it's showing you. So I'm going to change this one to unique values because there's actually only eight different values that can be. There's 256. I must have done this a little bit differently than I thought. Unless. Let's see what the count is of each. Anyway. Well, typically it represents which direction it's going. So you could think about that as which direction the slope is going. So that's why some of these have the same value. Now, the reason that there's so many of these is because sometimes you can model all the different possible combinations. It's flowing in every direction versus it's flowing just north and just west. And if you do that, there's actually 8 to the third, because there's three rows and 3 columns. So there's 2 to the 8th different choices. So there's 256 different combinations. So I thought this was just going to be 8 different combinations, but it has every single different direction accounted for it. But in any case, that's unique value. Every raster has a value assigned to it that's a unique color. And I could change any of the individual colors. Oh, actually I should have done the land cover, because that would make more sense. That's what I meant to do. Sorry. That's the data set I was planning to use. Okay, so land cover is a little bit coarser data set, but every cell represents what the land cover is. And so I've got a color here that looks like, see this kind of teal color? That represents scrub shrub. I might not want to display scrub shrub as that color. I might want to display it as kind of a brown color, because that's what color it is most of the time. That's why it burns so well. And then forested displays as green. There's not a whole lot of forested area here. There's some mixed, and there is some evergreen. Evergreen, I might want to display that as actually green. So these are some evergreen areas. And then it's typical to display developed as either a gray or sometimes a red, depending on who you're doing. So I'll make a couple of these gray real quick. I made that one red. I'll make it gray. All right, so what I'm doing there is I'm, in all of these cases, everything I've been showing you about symbology, what it does is it modifies the path from the raw value number values to the digital number values that get turned into red, green, and blue values on the screen. And so that path is actually referred to as a lookup table. So the input values are the raw raster values, and the output values are the RGB values that are being displayed. And so every time you change this, you're modifying what's referred to as a lookup table. So one more thing with this data is this data set does have a attribute table associated with it. But you can still see that the values that are stored in the raster are in this column. This is how many of those there are. And then this is another attribute that's been assigned to that value. I could have another one called description that maybe had a whole blob of text associated with it that would describe what developed high meant. Because we can kind of picture in our mind what developed high is, and what developed medium is, and what developed low is. But if we wanted a specific definition, we could have that. Alternatively, that might be in some other metadata file. But you can still have as many columns as you want in a raster attribute table, is what this is referred to. The raster attribute table. So I could add, I could use my geoprocessing tools to add data to that column. Okay. All right. So that's displaying raster data. So the raw numbers that's stored in their files, they have to be transformed into 3 8-bit values. Whether or not you actually see that, so like when I click on here, it actually is telling me that the unique value is 12. It's not telling me what the RGB value is. If I want to find that out, I would have to cut and paste it into Photoshop and click on it and get the value. Or actually, you know what? It'll show up here. I think I can do it right here. So I can go in here and change the color and go to color properties, and that is the RGB value that's showing up right there. Okay. All right. So no matter what data set you're dealing with, whether it's a floating point, whether it's integer, whatever the bit depth is, the summary here is that it has to be displayed to the user as red, green, and blue, 8-bit red, green, and blue values. You don't always use color. Sometimes you use black and white, in which case it's displaying the same red, green, and blue value. But there's still a red, green, and blue value. So your lab kind of walks you through this a little bit and asks you a few more questions about it. Okay. You'll have to answer. All right. Wow, it's already 4 o'clock. We do have a. All right, so we're gonna talk about here is raster analysis and how it's done in ArcGIS, and then specifically what we're going to introduce the concept of a raster function. You may have already run some of these, but we're going to show you how to do it a few different ways in ArcGIS Pro. So there's a lot of things on here. You guys can just save this for later. I'll just go ahead and demonstrate this. Okay? So this is we've got our data up. I'm going to kind of move this down, and then get rid of the attribute table. I don't need that. Yeah, there we go. Okay, so I got rid of the attribute table. So with what those arrows we're trying to point to is that there are actually a few different ways to interact and to do raster analysis in ArcGIS. Okay. And let me see, which one? So I'm going to start with the toolbox, because the toolbox is kind of the oldest way, but it's still maybe the most common way that people interact. Because GIS, when it was first conceptualized, got people thought about it, and they liked using it as, or they liked to think about it as a collection of tools. So these tools are basically different functions where the inputs are layers and the outputs are new layers. So if you go to analysis on here and you click tools, then this will open up. So let's close it. I'm going to click tools again, and that geoprocessing pane opens up. So one of the primary innovations that ESRI kind of sold everybody on was this vision of linking up GIS tools in order to do analysis. And so we have this huge toolbox full of tools. We are going to be focused on this thing called Spatial Analyst. Spatial Analyst is the toolbox for working with raster GIS data. It's the primary tool for doing that. Of course, there's some tools in data management that we're going to want to utilize, because data management has tools like for combining two raster data sets. That's map mosaic data set. It's like taking two data sets and making them one. There's copy raster for copying a raster data set. You can also do that by just going into catalog and copying and pasting like you'd expect. Okay, but the spatial analyst tools are those tools that are dedicated to working on raster data. And in the lab, I point out that all of these tools are basically just doing math on the rasters. So the rasters are all numbers, right? We've already established that. This is just rows and columns of numbers. If I want to ask the raster a question, I need to think about how a mathematical formula answers that question. So, in other words, if I want to ask the raster what what are all the areas above a certain elevation, then I need to think about what mathematical formula answers that question. So, what mathematical formula does answer that question? Find me all the elevations above 300 feet. What's another way to say that? X equals something. Yeah, X equals all the areas greater than the value, or let's just say X equals all the values in the cells. So I need a statement like if X is greater than 300 feet, do something, right? Assign the values 1 or assign the values 0. So there are actually a few different tools for doing that. Next week's lab will get you a little bit more detail in that regard. But most of this can be done in a lot of these basic types of questions can be done in raster, what they call raster calculators, a tool called raster calculator. So if you go under spatial analysis tools, go under map algebra, click raster calculator. Raster calculator allows you to do math on rasters. In fact, one of the other things I say in the lab is that most raster analysis just is like a you have to figure out, it's like a story problem with two-dimensional, sometimes three-dimensional, but map data with raster data sets. It's like a story problem with raster data sets. Okay? So we've got our elevation data set, and we want to find out what elevation data set, what values are less than a certain value. We could say elevation is less than, and what did I say, 300 feet? So how many, let's just round it off. That's what 100 meters about. So we know that the data set is actually in meters. Anybody know the exact conversion to meters? Did I say over or under 300? Over. So if I want over, I should actually do this. Greater than, I'm going to say 300 here. Watch this. So I'm doing more math. It's approximately meters. 0.3048. Pretty sure that's out to 4 decimal places. So this is meters. You multiply it by 0.3048, and I'll get feet. I meant to put this parenthesis right there. Okay. So what I'm doing is I'm taking elevation, I'm multiplying it by 0.3048, and I'm saying, is it less than 300? Is that value less than 300 feet? So I should be it's actually the other direction. I'm going the wrong way, right? So 1 meter in feet, so 3.2. All right. So now I got the conversion right. 3.28084. So what I'm going to do is take the elevation value, multiply it by this to convert it into feet, and then say, is it less than 300? Or greater, is it greater than 300? And this is my output raster. And by the way, it's going to store that. See, by default, it stores that in that database that we set up. So I'm going to call this, high areas. I'll call it LB, high areas for Long Beach. Don't put spaces in your file names. You can, but it always causes problems. So I never do. All right, run. So it's running, and it's going through every single cell, and it's finding out if it matches that criteria. So now in my new output raster, I can click on it, and the data here, the value here is going to be 1, and the value here is going to be 0. Now ESRI had to decide to do that, right? Like, I didn't tell it, make 1 above and 0 below, but that is actually the convention for a few different programs, that true is 1 and 0 is false. So if the answer to your mathematical equation is true and false, then the zeros and the ones will. And the reason that is because if you multiply 0 by anything else, what happens? You get 0. Okay, so we could use this as a mask to get rid of non-zero values, everything else. What if you multiply anything by 1? Right. So if I go to a different tool, well, if I just multiply the land cover in the high areas, and I multiply that, by the way, computer science asterisk usually means multiply, in this case it does too. I multiply that back to the elevation values, and I run it. Nope. I'm going to call this mast lows. So now I run this, and let's display this. I'm gonna do something in the symbology. Sorry, in the symbology, I'm going to display background 0 as no data. It's displayed as clear. So it's my background value. So now what I've done, you're seeing the other layer behind it. So what I've done in my output data set, I've masked out. It's still elevation values, but I've masked out everything below a certain value. So I'm ignoring it for whatever reason. It might be that in order to ask a question later, there's a reason to do that. I might want to know what the average elevation is that's above 300. You know, there could be lots of different reasons why I did it, but I did it. I'm showing you how to manipulate GIS data, and that was through the geoprocessing pane, what we call our toolbox. The tool button right here got me to that. The toolbox. All right, now you can actually do almost any other operation that you can do here. So for example, if I expand math, you're going to see times. Times, if I click on it, it just allows me to multiply two rasters. I can do that in the raster calculator. I can do it in there. I could do absolute value. I could do float. Oh, float and int, by the way, convert back and forth between floating point and integer. So if you have a floating point raster and you want to convert it to integer, you could just run just this tool. We have, so for example, if I decided I don't really care about the elevation data, I don't care. I just want to know what meter it is. I don't care what the sub-meter part. So I could just go, just call this int elevation and run it. And now I've got a new data set, and when it pops up here, you'll see that I no longer have the decimal place out there. But let's say I did want to do that thing I described earlier. I can go back to raster calculator, and int is a function. Like I said, almost everything you can do right from raster calculator. So int of the elevation data set times, or no, I wanted to multiply it first. Multiply it by 100 before I do the integer conversion. And now I run this, and I'm going to call this integer elevation centimeters, 10 decimeters, centimeters, yep. So now I have elevation in centimeters, but I don't have such a big data set because it's an integer data set. If I look here, maybe not though. Let's see if I save myself into that. No, it's still a 32-bit data set. So I didn't save myself too much room, but maybe if I had restricted myself to, let's look at this one though. Maybe depends on what they see. That's ArcGIS ESRI thought about it and said, okay, what's your minimum and maximum value? So when I converted the original data set that ranged from 2 to 295, it said, oh, you only need a 16-bit number, integer number, to store all your different possible values. So I'm going to make your output a 16-bit data set, so it is smaller. However, my centimeter data set is not actually any smaller than my floating point data. They're both 32-bit numbers. It's just one is an integer number and one is a floating point number.
What about the above and below 300?
Oh, well, yeah, I mean, a smaller floating point?
Yeah,
Probably not, but let's see. No, I kept that as a 30.2 point. Because that time I was worried more about precision, and in this data set, not for any real good reason, I do have I do have, go back to the, no, I still have centimeters, millimeters, whatever that is, I mean, like, not any real elevation changes out there aren't. So yeah, so that is, that's the raster calculator. The raster calculator has, you know, everything that you'd expect to see on a normal calculator. There's the ability to do plus more. There's more, and that's the kind of things that we'll be talking about later on in this semester. Okay? So that's what these the remainder of these slides kind of introduce this concept of raster map algebra. We could combine multiple data sets, which is one thing that we did. We multiplied the mask data set times the original elevation data set to get this data set. Okay. This concept, which you should read about, you know, go back through these slides and read. I have Tomlin's original it was written in the 70s, research article up on Canvas for you to read, where he introduces this concept of map algebra. Okay, and then I also have it presented in a textbook. The textbook is called GIS Modeling and Raster. So go read those two. That's not too much reading. Next week there's a little more reading, but these are pretty short. So yeah, one of the ways that you can kind of think about this as a little more fun way is that we're combining these different data in a map sandwich. One thing that this does point out is that, and I tried to show it when I did the operations in ArcGIS Pro, is that you are letting ESRI do some things for you. There are some assumptions being made about the layers. And those assumptions get magnified if you start getting sloppy with cell size and projection information. And so you do have to pay attention to that. So when we're talking about multiplying two different data sets, if they don't have the exact same cell size and the exact same extent, you're asking ESRI to take care of that, and it does have some defaults. By the way, you can change those here if you go under environments. So you can change if the cell sizes are different, you can have it reconcile it by making it the maximum of inputs, the minimum of inputs. You could select a few different ways, but even then, you're still letting ESRI decide which cells line up exactly with which other cells. It's going to choose the nearest one by default. And then also, what will the output be? What will the output coordinate system be? Well, that you can change right here. Is the output going to be coordinate system A or coordinate system B? Now, a lot of the times, it actually does not do the coordinate system transformation correctly. So I think the best practice is to at least make sure that all of your raster data is stored in the same projection before you do analysis. Because I've noticed a lot of glitches, and sometimes it just craps out. It doesn't even work. Probably because it's doing a heck of a lot of math in the background to convert, because it has to convert the location of the center of every cell. And that's a lot of math, because it's not doing it as it's calculating each one, but it has to decide which of these two data sets is the output projection. If the output projection is actually a third projection, then it has to convert both of the input data sets to that projection. And it does it in a cell by cell. It builds the new cell, it builds the new raster out, and then it transforms to which cell is the closest to the middle of this new output coordinate system. It's a big mess. You might have done it in your remote sensing class when you talked about resampling, but there's a big transformation that occurs. So the best practice is to do that transformation first and have all your data in the same projection. How do you do that?
Director,
Yeah.
well, if you're pulling from a geodatabase, isn't all data inside a geodatabase in the same, or isn't it supposed to be in the same projection? Am I wrong on that?
It doesn't have to be. Now, there is something called a raster catalog or a mosaic data set, which I alluded to before, and in those cases, they're kind of like feature data sets where they all do have to be in the same projection. All have the same cell size.
Feature data sets that have to be in
Yes,
the same
all feature data sets and all mosaic data and raster catalogs, those all have to be in the same projection, but they don't have to have the same cell size, and they don't always have to have the same corner, okay? The same. So let's see. Well, for example, zoom in way in here. So look at this data set right here. Which data set is that? That is the Laguna Beach image. That's this one. I'm going to go ahead and change the symbology back on that one. Okay. So look at that one. How it's one cell off. It looks like. I think that's one cell off. It's one cell different, okay, which isn't a big deal. I mean, most analysis that wouldn't be a big deal, but you got to account for that, or sometimes you might see just one raster cell different. This snap raster, if you set the snap raster, what that does is it makes sure that the output data set has the same coordinate system, the same cell size, and the same corner as the input data set. So the snap raster will ensure that the output looks exactly like X data set. So if you ever want to take data set A and keep all of data set A's characteristics, except you want it to look exactly like data set B. You want it to have the same cell size, you want it to have the same corner, you want it to have the same projection information. One thing you can do is set the snap raster to that data set B and then take data set A and multiply it by 1. It'll just force it into the same data set. So for example, I could because there is one data set that's different, and that's this one. So we got land cover, right? And turn off this one. Is that even on? Yeah, there's land cover, and you see how different it is? It's in a different place. Let's say I want the elevation data to be sampled to up to 30 meters, because this is a 30-meter cell size, I'm pretty sure. Let's see what it is. Let's say I want that. Yeah, 30-meter cell size. Let's say I want the elevation to be sampled up to 30 meters because I'm interested in doing that. And I want to explicitly know how it affects my data in further analysis. Then I could go to Raster Calculator. Under the environments, I can make sure that the snap raster is set to the land cover data set, because that's the data set that's going to get it's going to get all the properties of, and then go back to parameters. Don't go back to Raster Calculator because it'll reset this. So make sure you go back to parameters, because now it didn't reset that. So go back to parameters, and you could take the elevation data set and you can multiply it by 1. Something I like to do for fun, I'm not sure if this matters, but is to make sure that is a floating point number, if I want to preserve the fact that it was a floating point number. And then I'm going to call this output 30-meter 30-meter elevation. I don't know if it'll let me do elevation 30-meter LB stands for Laguna Beach. All right. Oh, for some reason that didn't work. Back to environments. I said snap raster land cover. Maybe it forces me to, but I did have this already set to max. Oh, cell size. I thought that it forced it to do the land cover, but I guess not. So snap raster, maybe it's just about the corner. So let's see if this works. Hopefully this works. So the corner and the projection is snap raster. Let's see if the output data set will work. Yeah, so that did it right. So you do have to set the cell size independently. It doesn't fix it as well. So in your environments, if you want it to match exactly, you set the land cover and the cell size. If I didn't select the snap raster, if I left that blank, the cell size was the same, and I run it, it's going to use the old corner as the new corner. It's probably just remembering my it's probably just remembering the last time I ran it, so it's not saying what it should do. But it would run correctly if I hadn't run it yet. Okay. But sometimes it's important to make sure that they're exactly coincident with each other. I think it is. Let's see if these are exactly coincident with each other. So I've got land cover and elevation. I turn them off. Yeah, they're exactly the same as each other. I could have done the same thing with the raster bands, the image. Now, if I hit image LB, let's say I multiply it by 20, just for fun, and save this as image MULT. If I run this, it's going to create an output that is actually not what I expect. So sometimes it's hard to deal with multi-band rasters in map algebra. See how I put it? I don't know if it just took the first band or if it combined all of them. I wouldn't deal too much with multi-band rasters directly in map algebra. The best way to deal with multi-band rasters in map algebra is to add them as an individual band. You can do that if you go over, I think you can do it from the catalog. If you go to image LB and you expand it, you can add just a single band. So now I've got just the red band, and now that'll show up here. See, I've got just that one band. Because I told you before, the individual bands are actually really rasters themselves. So to do raster calculators on them, you want to explicitly know what you're doing. And so add the individual bands to the raster calculator rather than doing them as rather than using the whole raster data set, because you never know what you're getting. Okay, I'm sure you can find in the documentation how it's handling it, but even if it's handling it the way you want to this time, it's probably not doing it the way you'd want to in another application. Okay. All right, so that is raster calculator. Now that's the toolbox. Now, ArcGIS comes with the ability to chain tools together, and we practiced this in my vector class, but that's Model Builder. And we're not going to talk too much about Model Builder today. I'm just going to show you. It's right here. I could do what I did today when I ran both the times and the which one did I do? Oh, and I ran a greater than, right? I think we didn't even have this on here. We did it in raster calculator, right? I just want to show you that everything also is somewhere else. I think it's under local. Local, greater, No, that's. It's under logical. See logical? Okay, I can't find it, so I know what it's called though. Greater than. It's under, well, it doesn't tell me where it is, but I can just drag it directly from there. So I can run the greater than tool and say, is the original elevation data set greater than, for simplicity, I'm just going to say 100, which is roughly the same as 300 meters. I would actually have to do the times first, then the greater than, then another times to replicate exactly what we did. So then I say OK, and then I can chain these together. I can chain greater than to the next one, and it's the input. Oh, this is square root. I meant to do times. Then I chain together times, and I times it by the original elevation data set. Times that by the original data, and that would be roughly equivalent to what we did. We didn't do the meter conversion the second time, but that's roughly equivalent to that. What did I call this output? Times greater than 1. If I run this, I should get a data set pretty similar. It won't be quite the same values, but it'll be pretty similar to that. It's done now. Oh, now it's doing the second one. It says done. I think it's done. All right. And then I can add this to the display. And that's this one. And I can display this again with the symbology where I disable that background value. See how it remasks those areas? So I did that in Model Builder. Now you'll notice in Model Builder I chose to use the tools that are, I told you everything can run inside Raster Calculator, right? You could do times, you can do greater than, you can do almost any of these other tools, you can do them right in Raster Calculator. However, they're harder to use in Model Builder. It's easier to use the basic tools in Model Builder than it is to do the, you can put a raster calculator into Model Builder, but it's harder to use. It's harder to link everything up because all your data sets can be stored inside one big equation. So if you're going to use Model Builder, do it here, but lots of times you can take an entire model and you can boil it down into one equation that you can run in Raster Calculator. So those are two different ways to get the same thing. And then the last way that I'm going to introduce today, I'm going to talk about Python, but just a little bit. The last way is the new way for I'll just go like this. The new way for ArcGIS Pro, and that is to use raster functions. Okay. So raster functions are kind of neat. What they do is these are basically like the tools, but they're different because they create virtual layers on the fly of the data. And so here I do have mathematical operations. So I can multiply. See if there's one called greater than. Yep, there is. So I can run greater than, and I say that I want to run it on the elevation data set, and I want that cell size to be, so yeah, that's the default. Greater than, and then I just change this value to 100. Again, I'm not doing the feet to meters conversion this time, but if I just hit create new layer here, it'll make a new virtual layer. So that layer is only, say, if I hit save here, it actually doesn't put that layer on disk anywhere. It saves the function that was used to create that layer. And it puts everything, every time I want to pan or zoom or anything, it puts the original data set through that function again and displays it for us. I'm sure that it actually saves something in some temporary scratch space at some points if you have a really large data set. But if you have a small data set, it probably is doing this all in the computer's memory. Let's see if there's a, might be able to, so yeah, well, see the location that it still just says it's an elevation. See that? That's the actual source of this data, is the original data set. And so it's just doing this on the fly. But, so the advantage to that is that I'm not creating a bunch of temporary data sets on disk. And there is there is something stored in this project that basically tells how this layer got stored. Okay, so now I can actually chain these things together, and they still don't produce an actual data set on disk. So now if I want to do times, want to multiply it, I can take the output of this greater than elevation data set, and I can multiply that by the original elevation data set, and then create a new layer. And then I can still symbolize this however I want, but this is still the original elevation data set. Symbolize that, doing the same sort of symbology that we've seen. Actually, I'm gonna use a different color scheme, maybe like that, and then I do want to display the background values just to show you that they're 0. And if I want to actually save that out onto disk, I just say data export raster to actually write it out onto disk. But
Where do you do that? Oh,
right click on it
okay.
and say data export raster, and then it'll allow me to export it, and then that'll save a permanent copy. Now if I hit save here and I close it, I bring it back up, it recalculates it, so it's kind of like there's a real copy, but I can also, what's kind of neat and good about this is that I can edit the function chain. So I hit edit function chain, and I see, kind of like Model Builder, I see a chain that that represents what the process that was used to create that output raster, and I can edit it. I can change this value. I could change it to, let's say the real conversion factor would be that. So, no, it would be, I said 100. Yeah, so no, it would be this. Yeah, exactly. So that would be exactly everything below 100 meters would be that number. So now I just validate it and then run it again, and the result, is it taking a little while to run, or did I do something wrong? Let's see what the actual values in here are. Maybe it didn't like how that became a floating point number. Okay, that worked. You know what? I think I was just changing the label itself. Let's see if this works. 328, what was the number? Oh, well, yeah, I'm not really doing the right logic. I'm actually messing up because now 328 is actually bigger, 328 meters is actually bigger than anything. So I'm logically making the bad mistake. What I need to do is say what is 100 meters is 328 feet, but that's not the right question. I need to say what is I only cut it at 100 meters was the other thing that was cut at. So how many feet is that? Yeah. But anyway, I'm trying to get how many, yeah, that's what I'm trying to get. That's the number I need. So my logic was wrong. I'm trying to figure out how many meters 300 feet is. And so I was just backwards. So now this will produce an answer, and that answer is up there, and it's slightly different, but I can change the symbology back to that other layer and display the background. Whoa. Crazy color scheme. There we go. All right. So that's kind of cool because I don't even have to save all those individual layers out. Like I could do the same thing with Model Builder, but it actually takes longer to run. Now at some point, if the model gets really, really complex, you might just want to run it through Model Builder. Okay? But in my opinion, this has a lot more, when you're just dealing with raster data, this is a lot stronger a way to do it because it's all doing it virtually. And it's actually taking the graphical thing here and doing it in the most efficient way in the code. So what's actually being done, you're looking at it you're defining it as 2 steps, but in reality, it's not actually 2 steps. It's a single step, and it's running through there. The other advantage to this is that you can actually save the function chain out and then load it for a whole entirely different data set, which is the other reason for using Model Builder in the first place, is that it's portable. So now it's portable, you can export it and reuse a different raster. So I can just change the source for that data set. So I like raster function, what do they call them? Raster functions, and then they call these, when you've done multiple ones, they call them function chains. So you've chained multiple functions together. So comparing and contrasting them to Model Builder is actually something that I have a few questions about in the lab. But to sum that up, Model Builder produces a different data set every time through the process, whereas a function chain doesn't ever create a new data set until you tell it to create a new data set. And all of the numbers are just computed on the fly. They just travel through, it's like they travel through the function chain, they get to the end, and that number is displayed. So it's like adding extra, in my opinion, it's like adding extra processes to that lookup table process. So, here we have some lookup table information. That's kind of like just the very last step in this function chain. So you're changing the initial values. They're going through some functional lookup table, and then they're going through a display lookup table in order to be displayed. So just going through 2 lookup tables. Lookup table for the math and the lookup table for the display. All right, now finally, you can do Python coding down here. We're going to go through a lecture where I'll teach you some basic Python coding, but most of the ways that you're going to see for the Python coding, the best way to learn about it is to actually look at a particular tool and to go to the help for that tool. When you go to the help for that tool, if you scroll down, you can see the syntax for that tool. And then sometimes you'll even see a sample. So if we want to multiply a data set, this is actually doing that, multiplying elevation times 0.34. So that's actually converting the other way. But if I want to copy that down here, then I need to input my raster. So I'm going to say elevation. It's not. Elevation times, do I have that conversion factor still up? I don't think so. 1 meter, I want to convert it to feet, so I multiply elevation by this. And I could actually call it something like EL feet equals, and I hit enter. I don't know why that data set doesn't show up. It should, oh, there it did. It showed up that time. I think it's because I put that space there. Elevation. Oh, it's in quotes. There you go. So my syntax was wrong because it was in quotes. So Python is a programming language, and if you're good at typing out Python, it becomes kind of like a command line. So I just multiplied it, and here's the output right there. See how it created that EL feet right there from this command. And I did that based on the help right here. So yeah, I put it in quotes. Python, there's lots of things you can learn about Python, but one of the things is Python doesn't care if you have double quotes or single quotes. It's as long as you're consistent. Like you started with a double, you end with a double, you're fine. All the rest of this stuff matters more if you're trying to run the Python script from outside of ArcGIS, which you can. But we'll cover that when we talk about scripting. So to summarize, we've manipulated this layer using raster functions, which is what we're going to do in this course, raster functions, in basically 4 different ways. We used the geoprocessing window, which is just using a tool one at a time. We used Model Builder, which allows you to chain tools together. We used the function chains, raster functions, which we can chain together to create function chains. And then finally, we used Python. So those are all the different ways that we can do raster analysis, which is basically just manipulating the numbers in a raster data set. So that's what we did today. So lots of times Python looks similar to this concept where a new layer is equal to the function of an old layer. We just did times as the function, but slope is a function that we'll talk about this semester. Distance is a function we'll talk about this semester. There's all sorts of different functions. And we'll start with the basic operators. Like we've done some basic operators today. We've done some arithmetic operators, which are basically just your typical add, subtract, multiply, and divide. So here's adding the values, multiplying the values in 2 rasters. Here's adding the values in 2 rasters. But really, there's all the different arithmetic operators you expect to see on a calculator and more. Here's the mod operator. It's just an example. I mean, there's other ones in there, but the mod operator returns the remainder after a division operation. So you can go look at the help. The class is too short to like go through every single operator that there is. You can expand all of those toolboxes that I talked about. It's more important to practice identifying how to mathematically solve a raster GIS problem, and then figure out which tools will help us to do that mathematically. All right, we've got relational operators, which mathematical operators are used most often, but these are all really a type of mathematical operation. But this is what we did. They return ones and zeros, so they allow us to build logical tests. That's what we did with the greater than. So we could do not equal to, we could do equal to, we could do greater than, less than, greater than or equal to, less than or equal to. Those are all relational operators. Boolean operators. They are allowing us to take two different raster data sets and say, usually these are ways to combine the outputs of relational data sets. In other words, if we get one data set and we ask for greater than, areas that are greater than 5 in elevation and are less than 10 meters away from something else, then we would use a Boolean operator. We'd use the Boolean operator AND in that case. So what AND does is it says if either of the two data sets are true, if both of the two data sets are true, the output will be true. If only one of the data sets, see 0 is false, so if this is false and this is true, the output is false. If either of them are false, so this one's false, but that one's true, the output's false. So the cells here represent the exact same cells. It's as if they were stacked on top of each other. Okay. So those are Boolean operators. Logical operators allow for logical tests. The difference in these are actually not that used that frequently, but you can read about those. There are some combination operators, some Boolean combination operators. We'll talk about these a little bit later in the course. All right, conditional operators are one of the most useful operations. What conditional does, it's almost like combining a mathematical operator. It is like combining a mathematical operator with a logical operator. A relational operator. So a mathematic or arithmetic operator combined with a relational operator. That's what a conditional operator is. It's like adding an if statement. So if you want to say, if the value is over 300, then assign it this value. So by default, ArcGIS assigns it a 0 or a 1. But if you wanted to come up with your own numbers, that's what conditional processing does. And then finally, no data. Sometimes it's necessary to convert no data to a real data number, and sometimes it's necessary to go backwards. So sometimes we want to convert all our zeros to no data. And because sometimes 0 means something. Like what if 0 actually means, like in an elevation data set, what does 0 mean? Yeah, it means sea level. It can't mean no data because it means sea level. So if we convert everything to 0, then sometimes we're going to also mess up and convert some sea level values, or some existing 0 sea level values will still be 0. What happens if we did the opposite? Like what happens if we really cared, if we'd ask the elevation data set, find all the areas that are less than 300 or less than 100. Change those values to 0. Well, some of them would have already been 0. So, or change everything greater than 100 to 0. Then we'd have some upland areas that are 0. Plus, we'd have all the areas that were actually 0 as 0. Okay. So, anyway, the point I'm trying to make is that sometimes you need to consider what you're making 0, and that's why a conditional operator is sometimes better than using a raw logical operator, converting everything to zeros and ones. Sometimes you need to say, don't make it 0, make it 750, because I know there's no 750 values, and then convert that 750 value to no data. Or usually what ESRI actually does is actually converting it to negative 999. Not always, but a lot of times it's converting it to 9999. But inside of ArcGIS, sorry, I opened the wrong thing. If you look at this, you can actually see what the no data value is. It's in here. No data value is actually that. That's the minimum double value. All right. All right, so that's what we're going to do for the remainder of the course is kind of go through different map algebra functions, and we'll get more advanced and talk about what they're doing, and what it's going to do is help you to understand when you see a problem how to break it down into a raster algebra story problem and come up with a answer that you need. But some of the operators get more advanced. So like slope is what is the slope? How do you define the slope in a particular location? Like, how do you define? I'm asking that question.
What is it, how large the difference is between the elevations?
Right. So slope is how quickly the elevation is changing, and so slope actually requires you to look around. Right? So we need functions that look around. Talk about those in the coming weeks. And what if I want to find out the distance from a certain cell? That's another type of operation. These are all different types of operations, but they're all just different functions that produce a new layer. So you always need to think about what the raster values are going to be in your output layer. So you got your input layers, raster values, your output layers. Sometimes there's lots of layers. All right, so go ahead. Sometimes if these things get too big, they don't work. So I'm going to go ahead and stop the video, but I'm going to say a few more